Hello, greeting from me to you today. We are going to look at some few questions, 100 level questions that we often encounter in our exam on physics. These are multiple choice questions. Sometimes we know some of the answers by memorizing them or by having seen some manuals that answer them. But sometimes we do not actually know why those answers were chosen, if they are actually correct. So I'm here to show you some of the reasons why the answer that is correct and why the other ones are not correct. So stay tuned. Don't forget to subscribe if you've not subscribed. Like our video and share it for other students to actually get access to it. It is very helpful for preparation for exam. I will not be able to exhaust all today, but I will take it one after the other, and probably subsequent videos I'll be putting it bit by bit so that we will get it. Okay, let's start from one question here that says, what type of thermometer is suitable for measuring a high temperature greater than 2000 Kelvin? Now, 2000 Kelvin. 2000 Kelvin. You see, 2000 Kelvin is a very high temperature. As you can see, it's about probably 1727 degrees Celsius. Yes, it's about 1727 degrees Celsius, because if you have 273 to this, of course it's going to give you 2000. So it's 1727 degrees Celsius. So you see, it's a very high temperature, and for this temperature to be measured, now what determines the thermometer we use in determining the temperature of a body is the thermometric substance used in that thermometer. For instance, mercury in glass thermometer, you know that the thermometric substance is the mercury. That means that as the mercury in the glass, as the thermometric substance expands, it gives you the reading of the substance or the body you want to determine its temperature. And you know that if mercury is in a glass, there is a limited size of that glass. And of course, the expansion of the mercury in the glass is limited. It has a maximum point to which it can expand. And for any further increase in temperature, will definitely make the mercury to want to expand beyond the confined volume, and that will make the glass to break. So there is a limited value of temperature which it can read. Okay. For instance, the mercury in glass thermometer we use in our conventional laboratory cannot measure beyond 100 degrees Celsius, because that is the calibration given to it. So if you use such thermometer here, of course it is going to break. So what kind of thermometer is suitable to measure temperature up to 2000 Kelvin? Now the option we have here are number E, optical pyrometer, mercury in glass thermometer, thermocouple thermometer, platinum thermometer. Now, amongst these four thermometers, we look at the characteristics of the one that is going to be the answer. Of course, mercury in glass thermometer is out of it from what I have explained. A thermocouple thermometer is also out of it, because thermocouple thermometer is a thermometer that works with the principle of two dissimilar metals that has different expansivity, so that at a point one of the thermometric substance will begin to expand. And in fact, amongst all of these four thermometers I mentioned, the optical pyrometer, the mercury in glass thermometer, thermocouple thermometer, and platinum thermometer, it is only optical pyrometer that can determine the temperature of a body without having any contact with that body. So you don't necessarily need that is going to measure it, don't necessarily need to go and touch the body before you can determine its temperature, which is a very good advantage in measuring a very high temperature as 2000 Kelvin or 1727 degrees Celsius. It's a very high temperature. And you know what 100 degrees Celsius is. Just imagine you're boiling water, you touching it, then talk of 1727 degrees Celsius. Before you even finish measuring the temperature, you are gone. So it is very necessary that you do not have contact with the body that has this level of temperature. So an optical pyrometer is a very good answer. Another reason is that an optical pyrometer has a very high temperature range. Think of about 700 degrees Celsius to 3000 degrees Celsius. So it can measure between 700 degrees Celsius to 3000 degrees Celsius, and you see how high this one is, which is within this range. So an optical pyrometer is a very good measuring instrument to measure the temperature. Because there is no physical contact, there is no wear or tear, there is no melting that occurs in an optical pyrometer. It gives its measurement. It doesn't necessarily require to be on the heat to measure the temperature. Another very important advantage is that it has a fast response and it rely on radiation sensation. It rely on this radiation of heat, not actually being able to have contact. Like I've said before, each measurement is through radiation. From the radiation of the heat from the body can be captured by an optical pyrometer to give you the measurements you want. So it's a very suitable measuring instrument for this temperature. And then finally, it is not usually affected by environmental changes. Okay, a little change in environment doesn't necessarily affect the optical pyrometer, unlike other thermometers. So with these options, we now say that the right option to this question is optical pyrometer. Okay, we've gotten that. So let's look at another question. This one is a calculation question. It says, when a person has a high fever, the body temperature is about 102.92 degrees Fahrenheit. What is the Celsius scale? When a person has a high fever, the body temperature is about 102.92 degrees Fahrenheit. What is the Celsius scale? We have option A, 39.4 degrees Celsius, B, 38.2 degrees Celsius, C, 37.9 degrees Celsius, and D, 42.3 degrees Celsius. Okay, what we will do is, we know that the Celsius scale will have the upper fixed point to be 100 degrees Celsius and the lower fixed point to be 0 degrees Celsius. And then in the Fahrenheit scale, we have the lower fixed point to be 32 degrees Fahrenheit and the upper fixed point to be 212 degrees Fahrenheit. Sometimes there is a formula we use to in making this conversion, but there are plenty formulas that you don't need to cram the formula. This is a general method that even if it is a resistance thermometer that is used, you can actually convert the resistance to degrees Celsius, degree Fahrenheit with this scale, if you understand the scale. So this is the upper fixed point of degrees of Celsius scale. So this is its conversion in Fahrenheit. So if the body is 102.92 degrees Fahrenheit, which is between 32 and 212. So if we say here is 102.92 degrees Fahrenheit, then its equivalent in degrees Celsius, we can call it X. Okay, if that is the case, what we are going to do is that we are going to take the ratio of the difference in that order. So if we say here 100 minus 0, that is the upper minus the lower, all over this X minus the same 0, the middle minus the lower. We do the same here, the upper minus the lower, that is 212 minus 32, the middle one minus the lower again, that is 102.92 minus 32. So if we do that, we have 100 here over X is equal to 212 minus 32 will give us 180 divided by 102.92 minus 32 will give us 70.92. And of course, from here we can now simplify. If we cross multiply this times this and this times this, we have 180 multiply x, okay, will give us 180x equals to 100 multiply 70.92 will give us 7092. Okay, then we are going to now divide both sides of the equation by the coefficient of x, which is 180, such that x will now be 7092 divided by 180. And if you punch your calculator properly, or if you compute properly, x will be equal to 39.4 degrees Celsius. So this is it. So if you are doing this, if you are using this method, the advantage is that it is going to be able to solve any kind of conversion of temperature. You know, if it's a resistance thermometer, it is going to be in ohms. And then if you have to convert to degrees Celsius, all you need to know is to know its equivalent, the maximum fixed point of that resistance thermometer and the minimum fixed point of that resistance thermometer. Once you know that, you can actually use the scale to compare it and get what you want to get at a certain point. So that is the answer to this second one, which is option A, I guess. Okay, let's look at another question. Okay, this other question says a temperature rise of 10 degrees Celsius causes mercury to expand and rise by 4 centimeters in a thermometer tube. A temperature rise of 10 degrees Celsius. Temperature rise, that's the change in temperature, is 10 degrees Celsius. Will lead to the rise in the length of mercury in a thermometer to be 4 centimeters. Okay? If the tube cross-sectional area is halved, that is, if the tube cross-sectional area is halved, that is, the first measurement, that is A1, and the second measurement is A2. If at the second measurement the area is now halved, that is half of A1, the second measurement, the area of the tube is made to be half of the area you used for the first one. That is what that statement means. Okay? They now said the mercury will rise by, that is what will now be the rise of the mercury. Originally, when you use the area, cross-sectional area A1, the mercury rose by 4 centimeters. That is the length, increase the length of the mercury in the thermometric tube. Okay? Then, when the cross-sectional area of the tube is reduced, that is when you reduce it by half of the first one, what will now be the temperature? Of course, you know that cross-sectional area actually affect the rise of a liquid. For instance, if you have something like this, maybe this is a bowl, and you pour a 1 liter liquid and it ends here. If you get another tube that is like this, that has a narrow cross-sectional area, unlike this, you know that this same 1 liter you pour here, if you transfer it here, it will get up to this point. So that shows that the tinier or the smaller the cross-sectional area of a tube, the higher the length, the same volume. So, of course, you know that liquid rises by volume, but you cannot actually, by merely looking at it, determine the volume. So, it is length that you can actually measure from a tube. It is by calculation we'll get the volume. Okay, then in a cylindrical tube, we know that the volume of a cylinder is the cross-sectional area times the length of that cylinder. So if the volume, increase in volume of the first tube, whose area is A1, is V1, then V1 is equal to A1 times L1. Okay, that is, this L1 is 4 centimeters. Then if the volume is changed to V2, V2 is equal to A2 times L2. And then we were told that the A2 is half of A1. Okay, if A2 is half of A1, if we cross multiply here, it now implies that A1 is twice A2. These two multiply this. So A1 is twice A2. And I can comfortably say that A1 here, V1 is equal to, instead of A1, I will use 2A2 to replace A1, then times L1. Okay, remember that if it is the same temperature rise, remember it is the same temperature rise, the volume does not change. The volume, whether in a wide tube or in a narrow tube, will be the same, because the volume of the liquid is dependent on the temperature, not on the tube. Okay, since so long as this tube is the same type of tube that absorbs temperature the same way, the volume of the tube, the volume of the mercury does not change. Therefore, the V1 is expected to still be equal to V2, even though the cross-sectional area of the tube has been halved. So, see, and V1 is A1 L1, while V2 is A2 L2. Okay, and we have replaced A1 with 2A2, so we can use this to replace this one, so that we are going to have 2A2 L1 is equal to A2 L2. Okay, A2 L2, and then you can see that this A2 can actually cancel this A2, and then you have 2 L1 equal to L2, and our L1 is 4 centimeter. That gives us L2. So L2 is equal to 8 centimeter. So the length of the mercury will increase by 8 centimeter if the cross-sectional area of the tube is halved. When the cross-sectional area is A1, the length of the mercury increased by 4 centimeter at 10 degrees Celsius. Then when this area has been halved, the length will double at the same temperature. Okay, so the answer is 8 centimeter for that particular question. Okay, let's look at this other question. This one is not a calculation question. It says, which of the following is or are true about ideal gas temperature scale? Which of the following is or are true about ideal gas temperature scale? You know, an ideal gas is a perfect gas that everything is correct. You ignore every environmental impact on the gas. Okay, so look at all the options we have. Number I says, since it is which is or are, one or more will be correct. So look at this. The lower fixed point is the lower fixed point pressure is 0 at 0 Kelvin. Is it correct? Yes, it is correct. The lower fixed point pressure is 0 at 0 Kelvin. Yes, because it is an ideal gas. When the temperature is at 0, that is the absolute zero temperature. Okay, that's the absolute zero temperature. And at absolute zero temperature, that is thermodynamic temperature, the pressure of the gas is 0 because the gas is not going to be in motion. The particles or the molecules of the gas will be assumed to be at rest. Remember, it is in ideal situation. Okay, III says that the value obtained from the scale is independent of the gas used. Yes, in absolute temperature, absolute gas or ideal gas situation, the type of gas used is irrelevant, because in ideal situation, that gas is obeying ideal gas law, and the type of gas is not necessary. It does not determine how the gas will react. Temperature change maximum and minimum points of that gas because it is ideal gas. So the type of gas is not necessary. So I is correct. I is also correct. So let's look at the last one, which is IV, that says the scale does depend on the property of the gas used. Of course, if II is correct, if the third one, the last one I said is correct, that is independent on the type of gas, then it does not depend on the property. If it depends on the property, then it is dependent on the type of gas. So since it's III is correct, the IV is not correct. So the answer is I and III. Okay, quickly let's look at another one. This one is a calculation question and we have to be attentive on it. It says constant volume gas thermometer is used to measure the temperature of a liquid for a triple point reference pressure of 120 kilopascal. A triple point reference pressure of 120 kilopascal. So if this is the triple point pressure 120 kilopascal. The gas pressure of the body is measured as 150 kilopascal. The pressure is measured, that is heated pressure, is 150 kilopascal. Okay, this is the triple point pressure, that is the actual pressure, and this is the measured pressure. Okay, for a triple point reference pressure of 75 kilopascal, that is when the triple point pressure is 75 kilopascal, then what will be the measured pressure? The gas pressure of the same hot body is now measured as 85 kilopascal. 85 kilopascal. So when the triple point pressure is 120 kilopascal, the measured pressure is 150 kilopascal. When the triple point pressure is 75 kilopascal, the measured pressure is 85 kilopascal. Okay, let's see what we're asked to do here. The gas pressure of the same hot body, okay, is now 85 kilopascal. Sorry, we now say find the constant volume gas temperature. That means that the volume of this gas is constant. And we're looking for the temperature of this liquid at volume, constant volume gas. So what is the temperature? Temperature is going to be calculated using a formula we have that says the triple point temperature times the pressure, the ratio of the pressure, measured pressure over the triple point pressure, if the triple point pressure approaches 0, the limit of the measured pressure over the triple point pressure, if the triple point pressure approaches 0 times the triple point temperature. Since the triple point pressure is approaching 0, we do what we call extrapolate. We extrapolate. We use what we have to get what we do not have, okay? We are not going to have a direct substitution since the triple point pressure is tending to 0. So let us see how that is going to be done. So the triple point pressure ratio of the first one is going to be equal to 150 divided by 120. That will give us a ratio of 1.25, while the second one is going to give us 85 over 75. That's equal to 1.133. Okay. Now, using a linear scale, because this is the temperature increases linearly, so we are going to use a linear graph, the gradient of a line, which we have as y minus y1 over x minus x1 is equal to y2 minus y1 over x2 minus x1. And of course, this is y minus y1 equals x minus x1. If you cross multiply, this will come here, times y2 minus y1 over x2 minus x1. Okay, and from this, y2 is the pressure ratio of the second one, that is 1.133. y1 is the pressure ratio of the first one, that is 1.25. Okay, x2 is the actual pressure of the second one, that is 75, while x1 is the actual pressure of the first one, which is 120. So using these parameters, I said y2 is the pressure ratio, the second pressure ratio because of these two. y1 is the first pressure ratio. x2 is the actual pressure of the second. 2. x1 is the actual pressure of the first. So if we input here, knowing that x is the absolute temperature, that is when the triple point pressure is tending to 0, the temperature x will tend to 0, so that we can now get the y. Okay, so the y, when we get the y, it will stand for this, because this is what we are looking for. We know the triple point temperature of the gas, that is 273.16 Kelvin. We use that as this tends to 0, that is the triple point pressure is tending to 0, so the triple point pressure is going to be 0, and if it's 0, this x is gone. So if we make y subject of the formula, minus y1 will cross, and it becomes y1 minus x1 times y2 minus y1 over x2 minus x1. Okay, so y is equal to, I said y1 is 1.25 minus x1 is 120 times y2 is 1.133 minus y1 1.25 all over x2 is 75 minus x1 is 120. Okay, that will give us what? So if you compute this, you get a negative answer. If you compute this, you get a negative answer. The minus will cancel the minus, and this will be a plus value times 120 will give us 1.25 minus, if you properly punch your calculator, you have 0.0026. 1.25 minus 0.0026, and y will be equal to 0.939. So substituting in this, the temperature will be equal to, the triple temperature is 273.16 times the whole of this I said is your y from our analysis times 0.939, and that's going to give us 256.46 if you properly compute. Okay, finally for this video we are going to stop here. The last question, but not the least, we are going to see other ones in other videos. It says, which of the following is not a property of materials which changes with temperature? Which of the following is not a property of materials which changes with temperature? A says volume of liquid. Of course, from even the ones we've answered, you know that the volume changes with temperature. So the volume of a liquid rises or increases as temperature increases. Okay. Number B says length of a solid. Yes, in linear expansivity, when you hit an object, it increases in length. That is what we call linear expansivity. The increase in length by unit length by degrees Celsius or Kelvin rise in temperature is linear expansivity. So the increase in length, the length of a body is dependent on the temperature change. So change in temperature affects the length of a solid. Then C, color radiated by a material. Yes, the color of a body is also a characteristic that changes with change in temperature. For instance, if you heat oil, the color changes. In fact, if you're very fair, that if you work so much on a scorching sun, you will know that your body will tell it that something has happened. Okay, that is enough example to tell you that the color radiation is also dependent on temperature change. Okay, then D, boiling point of liquid. The boiling point of a liquid is constant. For instance, the boiling point of water is 100. So the temperature change does not determine the boiling point, but the temperature change can attain the boiling point. So if you heat a body, it can attain its boiling point, but it does not change because the temperature changes. So you should understand that it remains constant. For water, the boiling point is 100 degrees Celsius. So it now depends on the temperature rise to get to that point before the water begins to boil. It cannot change the boiling point of a substance, a liquid. So boiling point of liquid is out of it, and that is the correct answer, because the question says which is not the property of a material which changes with temperature. So friends, we are going to call it an end today. Don't forget to subscribe if you've not subscribed. Like my video and share it to help others see it. And if you subscribe, of course, turn on the notification button so that subsequent videos that come, you are going to see it. It is not going to do anything to subscribe. You're not paying any money. I didn't ask you to give me money. The only thing you will give me is subscribe. It will help us and encourage us to do more for you to have. Bye.